Hello everyone, this is Artin, and in this video I would like to present the paper titled Beyond Text, a deep dive into large language models' ability on understanding graph data. This research was conducted by Yuntong Zheng, and Liang Zhao at Emory University. Large language models, or LLMs, are well known for their ability to handle language tasks, but today we're looking at something different, how these models work and how these models actually work with graph structured data, which is data organized in a way that shows how different points or nodes connect to each other. Here's what we're going to cover. First, we want to answer the question of, can LLMs handle and make use of data organized in graphs? And secondly, the question of, can they do better than the usual models used for graph data? We will go through how the researchers set up their studies, what they found out, and what this means for the future of using AI to analyze complex data. So let's get started and see what the study tells us about the potential of LLMs beyond just dealing with text. This research explores an innovative application of large language models, commonly known as LLMs, which are typically celebrated for their strength in natural language processing. The study shifts the focus from textual data to graph structured data, a domain where graph neural networks have traditionally dominated. The core of this research lies in its rigorous benchmarking of LLMs against specialized graph neural networks across a variety of prediction tasks at different levels, namely node, edge, and the entire graph. This comprehensive analysis aims to evaluate whether LLMs can not only handle but also effectively utilize the topological structures inherent in graph data to enhance their performance. But why is this significant? The findings from this study could greatly change how we understand LLM's capabilities, extending their use beyond mere text interpretation to complex graph analytics. This opens up new avenues for research and potential optimizations in how we handle structured data in AI. As we proceed, we'll dive deeper into their methodologies and discuss the implications of their findings, shedding light on the strengths and potential limitations of employing LLMs in this novel context. In recent advancements within the field of AI, large language models, known as LLMs, such as Transformers, BERT, GPT, and their latest iterations, have shown remarkable abilities in processing natural language. These models, often referred to as foundation models, are versatile enough to be applied to a wide range of downstream tasks with minimal customization. They have set new standards in various natural language processing tasks like text classification, machine translation, sentiment analysis, and text summarization. What sets apart recent models like GPT 3.5, GPT-4, Cloud 2, BART, Llama, and Llama 2 are their emergent capabilities such as in-context learning and zero-shot capabilities. These capabilities allow them to perform exceptionally well across tasks they weren't explicitly trained for, including complex activities such as mathematical reasoning and operating question answering systems. However, the conversation about LLMs has predominantly centered around their applications in processing sequential text-based data. The real challenge arises when these models are applied to graph structured data. Graphs, which are prevalent in many domains such as social networks, knowledge graphs, molecular structures, and transportation networks, offer a different kind of complexity. Unlike sequential data, graphs contain rich topological connections between entities, along with nodes, edge, and graph attributes that need to be modeled. This paper sets out to explore whether the strengths of LLMs can extend to understanding and predicting outcomes based on graph structured data. To thoroughly assess their capabilities, the authors have conducted a series of empirical experiments comparing the performance of LLMs with specialized graph models like graph neural networks or GNNs, and the experiments covered diverse tasks across node, edge, and graph level predictions in various domains such as citation networks, social networks, and chemical networks. The central questions addressed in this paper are threefold. 1. Can LLMs process graph analytics tasks effectively, even without explicit graph structure? 2. How well do LLMs interpret graph structures to enhance the performance of downstream tasks? And 3. How do different tasks, dimensions, and dataset domains impact LLM's ability to manage structured data? The forthcoming sections of the paper promise an extensive review of relevant literature, detailed findings from benchmarking LLMs against graph data, and a deep dive into the implications of these findings. By altering input prompt formats and analyzing the structural data across different task dimensions, this study aims to reveal how effectively LLMs can extract and leverage structural information from graphs. This introduction actually sets the stage for a comprehensive exploration of LLM's capabilities in a domain that goes beyond their traditional applications, challenging their adaptability and predictive power in handling graph-structured data. In this section, we explore the landscape of research on large language models, or LLMs, applied to graph-structured data. Recent studies have started to investigate the capabilities of LLMs in this domain, but the field remains largely underexplored. For example, research by Chen et al. And Guo et al. Has shown initial attempts to use LLMs for node classification within citation networks. However, these studies were limited to specific datasets and did not fully explore the potential across various task levels and datasets. On the other hand, Ye et al. Fine-tuned LLMs to outperform graph neural networks, or GNNs, on particular datasets, highlighting a different approach from our focus, which is to assess the intrinsic ability of LLMs to understand and utilize graph structures effectively. Additionally, we'll look at the advancements in graph neural networks, or GNNs, and we should say that GNNs have been developed as a specialized approach for graph analysis, excelling in tasks by leveraging the connectivity and topological structures of graphs. They represent a standard against which we aim to compare the performance of LLMs, particularly in tasks like node classification, link prediction, and graph classification, where GNNs currently set the benchmark. This background sets the stage for the study, which seeks to provide a more comprehensive examination of LLM's performance across various graph-structured tasks, pushing the boundaries of what we currently understand about their capabilities in the complex domain. In the experiment section of the paper, the authors conducted a comprehensive series of tests to explore the capabilities of large language models, or LLMs, on graph-structured data across various task levels. They utilized 5 commonly used graph benchmark datasets, specifically chosen for their rich contextual attributes at node, edge, and graph levels. These datasets include Quora, PubMed, OGBN Archive, WordNet 18, and Reddit, each offering unique challenges and structures that test the adaptability and accuracy of LLMs in interpreting graph data. The experiments were structured to assess LLM's performance in 3 distinct areas: node level, edge level, and graph level tasks. This approach allows for a detailed analysis of how well LLMs can handle different types of graph-related information from individual nodes and their connections to the broader graph structure. For node-level tasks, the research explored how LLMs manage classification based on textual information embedded within graph nodes, like research paper titles and abstracts in citation networks. The authors noted that while LLMs like GPT 3.5 and GPT 4 show promise, their performance still generally falls short of traditional graph neural networks, which have been specifically optimized for such tasks. In edge-level tasks, The study focused on link prediction capabilities, crucial for understanding the connectivity and relationship strength between nodes. Here, the authors found that incorporating more detailed structural information, such as neighbor node data, significantly improved the performance of LLMs, suggesting that these models can effectively use relational data when available. Finally, for graph-level tasks, experiments were conducted using the Reddit dataset, where each group represents a community or subreddit. These tasks tested the LLM's ability to classify entire graphs based on the aggregated textual content of posts within a community. The results highlighted the challenges LLM face with complex graph structures, particularly as the number of potential classifications increases. Overall, the experiment section outlines the rigorous testing framework the authors applied to evaluate the potential of LLMs in handling diverse and complex graph data tasks. It underscores the strengths and limitations of current LLM technology in graph analytics and set the stage for future research aimed at enhancing LLM's graph understanding capabilities. In concluding their study, the authors summarized the significant insights gained from their extensive empirical evaluation of LLMs on diverse graph learning tasks. They underscore that while LLMs such as GPT 3.5 and GPT 4 demonstrate promising capabilities in interpreting and leveraging graph structural information, their performance varies significantly across different task levels. There are a few key takeaways here. About node classification, we should say that LLMs show reasonable performance but still lag behind GNNs, which are optimized for such tasks. In the realm of edge prediction, incorporating structural data into LLM prompts notably improves their predictive accuracy, occasionally even surpassing traditional GNNs. And for graph classification, we should say that LLMs struggle with more complex graph structures, particularly as the classification complexity increases. The research highlights the inherent potential and current limitations of LLMs in graph analytics, emphasizing the need for further optimization to fully harness their capabilities in this domain. As for the future directions, the authors propose several avenues for future research to build upon the foundational understanding developed through this study. First one is enhanced benchmarking, which means more rigorous comparisons with graph specialized models to better understand the conditions under which LLMs excel. Second one is innovative prompt designs, which means development of novel prompt strategies that better exploit graph topological structures, potentially enhancing LLM performance. Next one is broader task exploration, which means expanding the range of graph-related tasks examined to include more diverse and complex scenarios. And the last one is model fine-tuning, which means experimenting with fine-tuned open source LLMs specifically for graph tasks to improve their adaptability and efficiency. In summary, this study provides a critical step forward in understanding the capabilities of LLMs in the graph data context, setting the stage for exciting future explorations that could lead to more sophisticated applications in graph analytics. Thanks a lot for watching this video, and I hope you enjoyed it.